Welcome back, everybody. So we're kind of finishing up section 1.1 today, getting into the meat and bones of it, which is really trying to figure out how to create differential equations. That's the tricky part most of the time. It's actually my least favorite part about differential equations as a whole is just trying to create it because the perspective that you have to take becomes really less mathematical and more intuitional. And you just have to think really hard about what a system is doing, make sure you account for all the variables, and then take some limits and cross your fingers that you did a good job. But we're going to go through some examples, and we're going to just try to get better by experiencing enough examples. So let's recall what we did in ODEs. We'll start just with ODEs and remark that an initial value problem, or really a problem that evolves in time, should be described as a function of time, t, and then a collection of derivatives of the position that we're looking for. So x is some vector in a d-dimensional space. And most of the time you can think about it as a position of something, but it could potentially be some other quantity. And that vector evolves over time, and you're thinking about how do all possible derivatives in time of that position interact with each other. So that's really what f is doing. F describes the interaction of derivatives with each other. And so we have some sort of interaction between all of these derivatives, and we basically set it equal to 0, saying, okay, whatever, if it's actually equal to 25t, we just bring it to the left-hand side of the equation and include it in f. So you can always set equations equal to 0 just by moving terms to the left-hand side. So that's why I say that's a generic version of one of these ODEs. And yeah, we're going to try to relate velocities, acceleration, and jerk, which is a higher order term, and so on, to each other, and trying to set it equal to 0. On the other hand, we also have boundary value problems. I mean, everything kind of looks the same, even with boundary value problems. Now I'm saying that our independent variable is x, so something evolves over space or it differs over space, and we have some quantity y, which exists in a d-dimensional space, and we're looking at how the derivatives over space. This is really the slope. It itself is the shape, but the slope over space or the curvature over space and these higher order derivatives over space, how do they all interact with each other to describe some quantity we're looking for? So that's what we want to think with ODEs. You either have acceleration and velocity over time, and you're going to compute a relationship between accelerations and velocities to solve for the trajectory of something, or you're going to find the shape of something by thinking about how maybe slopes and curvatures interact over space and then solving that problem. So let's look at one of these situations with time. This is the harmonic oscillator, which is a very classical example in both physics and in ODEs. And it comes from us talking about a mass on a spring, right? So we're going to basically grab a spring and put a mass at the bottom of it. And what we do is we pull down with some force. And actually, let's just call it a displacement. So we pull down with some displacement right away from the equilibrium. Let's call 0 the equilibrium. So 0 is the equilibrium, and we pull it some displacement away from the equilibrium, and we let go. And because of the restoring force of the spring, the spring is going to oscillate up, and the mass is going to oscillate up and down around this equilibrium. If there's friction, then of course it'll eventually come to a stop somewhere in equilibrium. So the question becomes, how can we construct an ODE which properly represents the situation? And with regards to really any sort of ODE, we're going to be thinking about cancellation of forces. So there, Newton's second law of motion tells us that F equals ma. So we're gonna come up with forces that cause the acceleration of this position, and then or forces which act against the acceleration of the position. We're just going to add them all up, set it equal to 0 because all forces add to 0, and then see what results. So the acceleration is just going to be some force, F acceleration, is going to be ma, but really this is mx double prime, right? So two derivatives in time of position will be our acceleration. So that's just going to be what it is. We have some mass, we have some acceleration, that's going to be that term. We now have to think about all other forces which might cause the acceleration, okay? And a very important force, I'll redraw my spring here. A very important force is the spring constant force, which comes from Hooke's law. And Hooke's law says that the spring constant, k, times the displacement, gives us the restoring force of the spring. Right, and so there's one force here which is causing acceleration, but there's actually a force that's going to be produced dependent on the displacement away from equilibrium that we are. There's also perhaps going to be some sort of friction. I mean, this friction could come from the spring itself. It could be that the mass is embedded in a fixed substance like honey, so we get some viscosity going along. But one way or the other, there's going to be a force which is proportional to the velocity, right? If I'm trying to travel really fast if you even try with water, if you move your hand really fast through water, then the force against your hand becomes higher and higher the faster you move it. And so friction force is proportional to velocity, and we can represent that instead of representing it as v. The same way we didn't want to represent a earlier, we do x double prime and we do x prime because we're relating derivatives to each other. And perhaps there's an external force as well. Who knows? Maybe the entire spring equilibrium is being shook, which is going to cause a force to be added to everything. Or maybe we put some thrusters on the mass. But whatever, there could possibly be an external force as well. So we've got this collection of basically a bunch of forces, and we're going to add them together. They all need to cancel out, right? This is how physics works. All forces need to cancel out. We don't necessarily know the signs on every single force, though, right? So it's going to be plus or minus depending on the direction that they all move in, and we have to be a little bit more clever at figuring out which directions they should be. And the way that I like to think about trying to figure out positive or negative on each of these forces is we put the acceleration force on one side of the equation and move everything else to the right-hand side, because we can just define this one to be positive, say, hey, I'm going to accelerate in the positive direction, whatever that means, and I want to figure out if these masses or if these signs should be positive or negative to affect my acceleration. So the question is, does the spring constant the force of the spring, does that act in the same direction or the opposite direction from acceleration? And it's not too hard to figure out that the spring constant acts in the opposite direction to acceleration. If I'm accelerating away from equilibrium, the spring constant's restoring that. The same with friction. And external is up to us. We just have to decide if the external force should be considered positive or negative. Just choose a direction and see if the external force agrees with that direction. So this one's up to us, but these other two both have to be negative, which is why if I jump down here, we can see that I've set up the acceleration to be of opposite sign to the restoring force and the frictional force, and I just decided the external force could be positive. Okay, so if we set this up in terms of all my x's, right, I've got mx double prime, this is my mass times acceleration. Here I've got the restoring force from Hooke's law, and I have a restoring force from friction, as well as my external force, and I rearrange that so that I have all my x's on one side, my force on the other side, and we start to immediately see the harmonic oscillator, ODE, that you probably were introduced in either physics or your ODEs course. We do want to set up an initial position and initial velocity. This would be like if I pulled it away from equilibrium and also pushed it in one direction right away. And so those initial values, the initial position will be x0, initial velocity, I'll give it the name x1. And we'll start our time at t0. So what we can see here is I've actually constructed one of these where I established that x0 was 1. Okay, so that's me putting a 1 right there. x1 is 0, so that's me putting a 0 right there. M is 2, so that's me putting a 2 here. Gamma is a quarter, so that's putting a quarter there. K is 1, so I put a 1 there. And F is 0, so I put a 0 there. So I've placed a lot of numbers into this. T0, of course, doesn't really matter much because you just start it from whenever you decide to start it, but I made T0 0 as well. And what is being plotted here is this is the mass itself. So you can see my initial mass is sitting at 1 there. And over time, right, there's a restoring force pulling me toward this equilibrium. And then I pass over the equilibrium. I pass right through it, and then I get to some minimum, and I start to oscillate back towards equilibrium. And in fact, over time, this amplitude is getting smaller and smaller. You should notice that that amplitude is certainly bigger than the later amplitude away from equilibrium. So I'm getting smaller and smaller. That's because I have a positive friction constant there. I can plot these all together, so I went ahead and plotted them all together, and you can start to see kind of the sine wave, which results from a harmonic oscillator. But of course, it's actually an exponentially decaying sine wave. The amplitude decays exponentially over time, and that's due to the friction. So this is a nice example of just using our physics principles, using Newton's laws as well as Hooke's law and our intuition on what should all of the forces on any given object to all cancel out in the right way, and then you get something that's actually physically meaningful, right? We get the oscillation of the mass around the equilibrium from the spring. Now that's a temporal problem, right? We were looking over time. How does this problem behave over time? How does the position change? But now we can look at a spatial problem. And with the spatial problem, I've brought up the catenary curve. This is a very common ODE that's often introduced in terms of variational techniques. This would be like with Euler-Lagrange equations, or if you ever study the calculus of variations. This is often a problem that gets brought up for that. And it's a question of, suppose I take 2 points in space and I put a chain between them, and then I let the chain fall. Now, of course, if the chain is taut between them, it can't fall anywhere, but suppose I put some bigger chain, which has extra length between them, and then I just let the chain fall. What does it fall into? What shape would it fall into? And it should fall into something like that, where it hangs. And it turns out that people didn't know how to find this object for quite some time. You would think maybe it's a parabola. It's not. It's approximated by a parabola, but it is not, in fact, a parabola. It's called this catenary. And so let's derive maybe the ODE that would produce the catenary for us if we solved it. So all we're going to do is name my variable y to be the height of the chain. And of course, the height of the chain should vary over space, right? So we're going to allow this height of the chain to be parameterized by space. And then we're going to fix the endpoints. So suppose I just have my endpoint here. I call this x0 in the spatial direction, and I call this one x1 in the spatial direction, and the height is going to be y0 here and y1 here. So that's the space, and that's the height. So I'm going to fix those points right away. This is how we discover boundary conditions. And then I'm going to try to figure out what are all of the forces that are exerted on the chain, right? And to do this, I'm going to actually introduce something that was probably not introduced in ODEs to you, but perhaps, depending on the course you took. It's called the continuum limit procedure, okay? The words come from the fact that we're going to take a limit of discrete points, which all have their forces on them. And under that limit, we're going to produce a continuum of points with forces. So the way this procedure works is we're going to start by choosing a number, capital N. Honestly, you could, of course, choose whatever letter you want for this, but I like capital N for a number of points. We're going to make these equidistant in space, and we're going to evaluate forces at these equidistant points. So let's just give a quick quick idea of maybe what's going to be happening here. Here's my catenary curve. What I'm going to do is let's do something like n equals 5. We're going to choose a number and we're going to do 1, 2, 3, 4, 5, 6. Now, this footnote comments on why I did 6 instead of 5. But you choose n equals 5, you end up with 5 plus 1. You technically have 5 intervals here, right? There's 1, 2, 3, 4, 5 intervals in the space, but the intervals are going to give you 6 points then. So we're going to evaluate forces at each of these 5 points, and we're going to give them this nice name, x sub n divided by capital N. So this would be something like x0, x1 fifth, x2 fifths, x3 fifths, 3 show up, x4 fifths, and x5 fifths, or x sub 1, right? So we've got our 6 points that we are evaluating at, and we're also going to call delta x kind of the distance of this interval. This should all feel fairly familiar for like standard calculus techniques that you may use, right? Because this almost feels like you're taking Riemann sums, right? You're going to discretize a function into so many points and kind of evaluate the value of the function at those points, except that we're thinking about forces now. So in step 2, we're going to calculate the forces exerted on these points. Now this is pretty nice. These boundaries, x0 and x1, you're allowed to really not think about them as having any forces on them because they're in equilibrium, so the total force has to be 0. They're at a boundary, they're fixed, they can't move around. The rest of the points, though, can all move around. And so we're going to be thinking just locally at x1 fifth, how much is it going to get pulled up? How much is it going to get pulled down? We're going to do the same thing for x2 fifths. How much is it going to get pulled up? How much is it going to get pulled down? x3 fifths, how much pulled up? How much pulled down? 4 fifths, up and down. And so we're going to calculate the forces there. We're not going to let these points move to the left or right at all, because this is the important part about the continuum limit, is that we're only evaluating up-down forces, and then we're just going to add points to the left or the right to calculate how things change to the left and right. So we're calculating these forces, F up and F down, on each of the points. So more or less, let's zoom in on one of these points on my catenary and see what it might look like very locally. Something like, let's make this, call this one x, n divided by n. So very locally, the only forces that are going to be able to pull me up are going to be from the chain itself, right? I'm going to get forces pulling from the chain itself. The force from the chain will be pulling on it up, and the force from gravity will be pulling it down. So somehow I'm going to have to calculate those forces, and I'm going to have to get them to cancel out. Because the system exists in equilibrium, right? We're waiting until the chain falls, and then it doesn't move up, down, left, right anymore. It's going to be in equilibrium. So eventually I'm going to be calculating the force of the chain at that point, and I'm going to be calculating the force of gravity at that point. Now, I'm going to continue ahead in the continuum limit method before I actually calculate those for the chain. The way this works is that the interaction of all the points and all of the forces, the points and forces, is going to give me a finite difference problem. Now this won't be a PDE or an ODE. It'll just be a finite difference problem. The notation's a little bit terrible here. What is it saying? F, as always, F will always be a relationship. Functions are relationships by their nature. So F's a relationship. What's it a relationship between? It's a relationship between my point, well, I guess this is the point I'm looking at, x sub n, and then its neighbor to the left, its neighbor to the right, the height to the left, its own height, and the height to the right. So F is some relationship of my neighbor, of my point with its neighbors, both in height and in left-right directions. That's all we're going to get. The interaction of all the points with forces will give me, hey, how is my point up, down related to its neighbors? Which makes a lot of sense with the chains being pulled. And you're going to go ahead and repeat those steps of thinking about the interaction of a point with its neighbors so that all forces cancel out. And you're going to let this capital N go to infinity, right? So if I jump back to maybe the catenary, if I start with 5 points, but then I move to, let's say, 20 points, in 20 points, I'm going to have something like this. I have no idea if I'm going to be able to fit 20 of these dots here. Probably not. But however many dots I manage to fit here right now, this will be a larger N. And you can imagine if I'm canceling all of the forces of all of these points, then as I do more and more points, I'm going to get a better and better approximation of how all these points end up. right? So it's going to be a point at which my approximation gets so close to perfect that it doesn't really matter. But in fact, in a lot of situations, we can just calculate what this looks like as n goes to infinity, how the forces behave as n goes to infinity. And what's going to happen is, because 2 points are going to get infinitely close together, but their heights are going to change by an infinitesimal amount as well, this will exactly give us a derivative. Or in some cases, maybe it'll give us 2 derivatives. In the first case, you can see that's a slope calculation. 2 derivatives will arise from a curvature calculation. Right. So that's what I have here. Any quantities of the following form, if I have my height evaluated at a point plus its neighbor minus the height at that point, and I divide by the distance to the neighbor, that converges to the derivative. This should look like the limit quotient, right? That is precisely the limit quotient. And then if you go through the procedure to calculate finite differences which approximate higher order derivatives, you find out that the second order derivative in a limiting definition looks like this. Okay, so I've got the height at a neighbor minus 2 times the height at a point plus the height at the neighbor to the left. So this is the neighbor to the right, the neighbor to the left. And you divide by the difference squared, you end up getting a second derivative. We're never going to go more complicated than 2 derivatives here. You can technically calculate this for infinitely many derivatives if you want to. This is called the finite difference method. And you can see my previous book on ODEs, which describes it a little bit more. But either way, as we take n to infinity, we are going to recover derivatives in y. That's kind of the important thing, is that derivatives in y will show up as we compute infinitely many points and the interactions between them. So let's actually see that in effect here. What we're going to do is we're going to fix our capital N, and we're going to fix our bounds. And we'll make the left-hand side y0. But we'll just make our lives easy and call this point 0 in space, this point 1 in space, the right-hand side, y1. And then we're going to choose our selection of points with a difference of 1 over n between each of them. So whatever that happens to be, it's just a difference of 1 over n between any 2 of the points. And what we're going to care about, like I said before, is we're going to zoom in on one of these. So we're going to zoom in on that, and we're going to ask ourselves the question, what does all of the forces look like? So we've got some tension forces in these directions. Tension from the chain will be pulling to the left and to the right, but it's going to be pulling in a slightly the upward direction, and we're going to have gravity pointing downwards. So the force of gravity pointing downwards is pretty easy. That's the mass times gravity. Remember Newton's law, mass times acceleration. Gravity always provides the same acceleration. So F gravity is always going to be mg. F tension is going to be a little trickier. F tension, what happens here is we end up with a slight right triangle. Right, there's going to be a right triangle here. The height will be to the neighbor. Right, what is the height between this point we're looking at and its neighbor to the right? So the height here will be y of xn plus delta x minus y xn. It's the difference in height. That's the height there. We know what the distance is to the right. It's going to be delta x. So we're looking at a right triangle with a height of y, x, whatever the neighbor's height is, minus y, x, and then the distance is delta x. So the total tension is going to be, with the Pythagorean theorem, the total tension in that direction will be the difference in height which is this, plus the difference in space squared, and you're going to take the square root of that. So that's going to be the length of the hypotenuse. It's going to be the square root of each of them squared. And so that's the direction in which the total tension is distributed in, the total force. But we only care about the force in the vertical direction. And so we're taking the ratio of the vertical change, which is given by that. We're going to take that divided by the total tension. So the amount that the tension exists in the vertical direction is exactly this quantity. And we can do this in both the left and right directions, right? But really what I want you to concentrate on is this giant quantity that I've just produced. This is the amount of tension that exists only in the vertical direction, because we care about the vertical difference on top, and we're dividing by the total length, which is where the direction the tension exists in. And if we do that both to the left and to the right, then we end up with here our force from gravity, because the local mass is proportional to the amount of the chain that we're looking at. And we're looking at 1 over n amount of the chain. We're looking at the force from the left tension here. We're looking at the force from the right tension here. And so here's where you can see these ratios of the vertical side of the triangle to its hypotenuse and the vertical side of the triangle to its hypotenuse. So these are the tension forces that show up. And then we have our force from gravity. What we're going to do then is we're going to construct this finite difference problem where all of the force, right, we set the forces equal to 0, the total number of forces equal to 0. So we make this finite difference problem here. And then we're going to take the limit as capital N goes to infinity. So I just want to talk about the denominators right now. If I isolate this denominator, this term doesn't look exactly like that denominator, right? So I've changed this term up a little bit from the original denominator. What have I done? I've actually taken 1 over n squared and I've factored it out of the denominator. So I've got a 1 over n all the way out of the square root sign. And then we end up with a 1 over n down here. And this becomes a 1. Okay, so that's where this is actually arising from. So you can imagine there's a 1 over n in a denominator that this limit is not actually accounting for. But what you can see in the limit that we're looking at, what you can see right here, is that this is the difference quotient, right? This is precisely the difference quotient we're looking for to give me y prime. And I can do the same thing with the other tension forces and get y prime there as well. That's only going to take care of the denominators for me. If I want to look at the numerators, I'm actually going to combine them together. And you'll notice what I have is I have 2 copies of negative y n over n. So here's my negative 2 copies of y n over n. I've got 1 copy of y to the left, and I've got 1 copy of y to the right. And then you'll recall that when I factored this term out here, I've got a 1 over n sitting around in the denominator here. And in fact, there's a 1 over n. If I divide both sides by 1 over n here, I'll get another copy of it in the denominator. And so I have a 1 over n squared in the denominator. And this was exactly the situation I was providing before about converging to the second derivative. So with that said, what I'm trying to say is that the denominators become this quantity, and the numerators become this quantity, so long as we've divided by that. Bring that to the left-hand side. And what we get then in the limit, in the continuum limit, is the ODE given by y double prime x over root y prime x squared plus 1 is equal to gravity. And there's my endpoints that have been fixed. Or in other words, I could potentially take the denominator, move it to the right, and square everything, and then we get this ODE. So one way or the other, those are the ODEs that we recover. If we go ahead and try to solve it with some special variables, 0 for x0, 2 pi for x1, 5 for y0, 7 for y1, and 1/2 for gravity. I just chose this because it made a nice picture for me. But you can see that is precisely a hanging chain. I don't think you could be ever more convinced about a hanging chain. Okay, so we're going to move on then to PDEs, where PDEs are allowing us to use a non-equilibrium temporal force, right? In the previous problem, we had to be in equilibrium over time. This doesn't change over time, even though it changes over space. With PDEs, we're allowed to be non-equilibrium in time, and we're allowed to change over space, right? So it's kind of a combination of, oh, not only can we think about all of the forces moving us around in time, giving us accelerations, but we can also change over space, and we can have a variance over space like the catenary had. So we get them both at the same time with PDEs. And so we'll look at an example here. This is exactly the same as the last example, except we're going to drop the rope. We're not going to assume that the rope was initially in equilibrium and stays in equilibrium forever. We're going to push it somewhere else right away. We're going to drop it and see what happens. Okay, so with that said then, this helps us understand initial and boundary conditions a little better, because in fact we inherit our boundary conditions from the previous case. We're still going to take a rope and fix its endpoints, but we're just not going to start it at its equilibrium anymore. We're going to start it away from its equilibrium. We're going to drop it and see what happens. But its endpoints are still fixed, so boundary cases exist where endpoints are fixed. That's how we can think about it. But once again, what is the boundary of time? The boundary of time is the present. So we're going to ask questions about what is the shape of the rope at the present. We're going to give it a name f. And let's make our life a little bit easier and say that the initial velocity of the rope is 0. We're not going to throw the rope from wherever we let it go. But it's going to have some initial shape f. So that's how we can come up with our boundary conditions for kind of combining these two together. And we can also ask a question about, what is the PDE that actually represents this situation? Well, let's interpret a rope as being a collection. If the rope has some elasticity, and suppose maybe our true equilibrium is this catenary, which we already know, the rope has some elasticity, and so actually any point on the rope will oscillate around equilibrium and eventually settle down, right? It's going to oscillate and eventually settle down at equilibrium. Well, if we studied anything that allows us to oscillate and eventually settle down to equilibrium, we sure have. We can do the same game as we did before with the continuum limit, except all we're going to do now is, instead of having all of my points in equilibrium, when I'm calculating the continuum limit, every point will be a harmonic oscillator. It's going to be a harmonic oscillator around equilibrium. And we could go through the full continuum limit process. We'd see the same thing happen, the same convergences happen. But what we're going to end up with is the following. We're going to end up with this PDE, where in fact we're covering the harmonic oscillator. This is the mass times acceleration, right? M times x double prime. There's my x double prime. We're recovering gamma times x prime. This is friction. Right, we've got friction going on. We've got acceleration, we've got friction. And what do we have here? This is a restoring force, Kx. Why is the Hooke's law restoring force the catenary itself? Well, think about it. This came from tension. This was tension in the rope, which we can think about as a spring, right? The rope serves as a spring around equilibrium. And so this is our Kx, Hooke's law, and then we have our external forcing. In the case of the harmonic oscillator is going to be gravity, or in the case of the catenary is going to be gravity. So one way or the other, we've got gravity on the right-hand side. And so we recover something that it oscillates in space and changes over, or oscillates in time and changes over space. And if we solve this problem, well, let's just set it up first. We can set it up as the following, just me directly grabbing my PDE. In the first line, here's my boundary conditions. So I've got at the boundaries for all time, I've got my fixed endpoints of y0 and y1. And then between the bounds at the beginning, I have the initial shape and my non-existent initial velocity. If I go ahead and solve this, and we'll learn how to solve this later this semester, what do we see? We're going to start the rope between the points 5 and 7 with an initial shape of 5 plus x over pi plus sine x. So that's going to be my initial shape, and then I'm going to let it fall. And if you see it, this is over time, the rope falls, and then it falls farther. And in fact, you can almost see, you should be able to see that this has moved to the right of equilibrium a little bit. That's because this term that was up high falls down, and it adds some velocity into the rope, pushing it to the right. And what we end up with is a rope which oscillates back and forth, but then eventually gets pretty close to equilibrium. So if you compare this equilibrium here to the equilibrium that we had calculated in the previous problem, they're actually really similar, but we can represent the shape of the rope over time rather than just the shape of the rope at equilibrium once we introduce PDEs. So this is really cool if maybe you're interested in simulation, even with video games and whatnot, because you can actually simulate real life physics, and you can get the computer to represent an actual falling rope and an actual gravitational field and reproduce the behavior exactly how you would see it in the real world. So anyway, those are a couple good examples of ODEs and PDEs that I wanted to share. Hopefully you start to feel a little bit better about developing these models yourself. I'll see you in the next class. Bye.